So let's take a look now at an idea referred to as the intermolecular forces. Now there are associations or attractions that take place between molecules. This is different from the bonds that hold atoms together that make up a single molecule. The intermolecular forces are those that hold together or attraction between the molecules. This is the famous quote from Obi-Wan Kenobi that all things in the galaxy are held together. And in fact, you could probably argue that what's holding together are the intermolecular forces. Now, matter has three states, gas, liquid, and solid. And these states are dependent upon the intermolecular forces and the strength that they experience between molecules. Gases, the strength of the force is very weak, and that's why the atoms or molecules in a gas can really have great spacing between them. When you get to a liquid, there is a moderate or mild attraction between the intermolecular forces between the molecules, and therefore the molecules can slide past each other, but they have very little space between them. And of course, in a solid, the molecules are locked into a specific position. And so the different states of matter depend upon the strength of the intermolecular forces between the molecules. Now, the intramolecular forces, I've been saying, is between the molecules. And here you see two water molecules having an attraction. And you'll notice that the distance between two atoms are 96 picometers, whereas the distance between the molecules is 300 picometers. So intermolecular forces are over a greater distance than you see between the bonds of atoms themselves. The intermolecular forces, they're generally speaking much weaker than the intramolecular forces, which are those that are between the atoms. But we must recognize that the intermolecular are actually quite strong. The different types of intermolecular forces are van der Waals forces, and there's actually two types. There are the dispersion forces and the London forces. There's also dipole to dipole attractions, hydrogen bonding, and ion dipole attractions. And so these are the different types of intermolecular forces that hold together these molecules to each other and influence what state they're going to be in, gas, liquid, solid. And what we're going to do now is we're going to walk our way through these different kinds of intermolecular forces and see if we can't get a handle on how they work. Here's a general summary of them. Dispersion forces are present in all molecules and all atoms, and what it represents is there is a momentary unequal distribution of the electrons in the cloud. And because of this momentary unequal distribution, there's a momentary dipole. There's a momentary region which is polar negative in the example given, that's on the left, and a region that is lacking them, which is polar on the positive. These things last for nanoseconds, but there is enough of a momentary attraction to create an association between the molecules. The reason these form is strictly statistical. It's just a random momentary clumping of electrons in the cloud. Now, a second type is a dipole to dipole, and this takes place as permanent dipoles. We have an unequal distribution of the electrons in the molecule permanently. And because of this, you can often get a stronger attraction between the two molecules, which is what you see there. There is hydrogen bonding, and in the case of hydrogen bonding, what you have is you have a permanent dipole, a permanent concentration of electrons, in this case at the bottom of the water molecule, which creates a permanent positive pole on the opposite side. And because of that, there's a hydrogen atom that sits between them. And that hydrogen atom effectively is shared between the two molecules. And that hydrogen sharing creates the hydrogen bond. And finally, you have the ion dipole. When you put the ionic compound, for example, salt, Na plus Cl minus, you have the water molecules become oriented in such a way that they surround the ion that is dissolved in it. And that's referred to as that ion dipole. Now, how strong are these attractions between these molecules? There is a variance in its strength. A covalent bond, which is within the atom itself, within the molecule itself, it's between the atoms. A covalent bond is extremely strong. Hydrogen bonding is less, as you can tell. Dipole to dipole interaction is further, and then your London forces are the least strong that take place. The London forces are those that are van der Waals. Those are the statistical unequal distribution of electrons. So at a given temperature and a given pressure, how strong the intermolecular forces are will determine what state the substance is in. If the intermolecular forces are weak, then at a given temperature, it will tend to be gaseous. If the intermolecular forces tend to be strong, perhaps more like hydrogen bonds or dipole to dipole, then you would find that the substance at that temperature tends to be liquid or solid. So let's take a look now closely at the first kind, which is called London dispersion forces. What creates them? Well, it was first developed by a man named Fritz London. And what it is, it's this temporary separation of charge that creates this momentary attraction. Now, it's between a non-polar molecule and its neighbors. So when you think about London dispersion, you want to think non-polar is what's going to hold it together, such as, for example, methane or butane. Those are non-polar molecules and are held together by the London dispersions. Now, the second idea is that the forces get greater, the London dispersion forces get greater when the molecules get bigger. And the reason why this happens is if you have bigger molecules, you have more electrons. And more electrons mean you can have a momentary unequal distribution is more likely. Think of a dance floor. We have only 4 or 5 couples dancing, and then you have a dance floor of several hundred. When you have several hundred on the dance floor, you're more likely to get pockets of concentration on the dance floor, and that momentary concentration would be a momentary polarity to that molecule and could create an attraction. So the larger the molecule, the more likely or the greater the London forces are. So what happens is this. You have non-polar molecules on the left. That's the A. And what happens is one of those non-polar has a momentary unequal distribution of electron. In this case, if you look over at B, the molecule on the left, you suddenly have a higher concentration of electrons on the left, lower concentration on the right. You create a polarity. That momentary polarity induces or creates a momentary polarity in its nearest neighbor. After all, the positive region on the left would create a negative region on the right because the electron cloud on the other one would have an attraction to it. And so in that instant, the polar positive, polar negative have an attraction, and therefore those molecules are briefly held together. Again, it's important to realize that this is an instantaneous event. In frame 1, you could see that the red dots, which are the electrons in the cloud, those red dots are unequally distributed, one closer in, one further out. And then you have in frame 2 a clearly equal distribution, but then in frame 3 you have a momentary unequal distribution, which by chance the 2 electrons are hanging out on one side, and in that instant that region is a polar negative, and in that instance you have a polar positive. Now when you have that, it's like a chain reaction. Look down below. When you look down below, you'll notice that the momentary negative and polar positive induces a whole chain effect down the line, and now you've created these attractions, and that will hold those molecules together. And the result is, rather than going to an instantaneous gas state, they would remain liquid, as an example. Here's another example. You have on the right, you have molecule A and B, it's non-polarized. Then you have an instantaneous dipole. Remember, the dipole means it's a polarity, negative, positive on the left and the right. And that's going to induce another one on the right side. And looking at it more as a cloud, that's the setup on the left with the blue or purple. You can see again the instantaneous dipole creates another instantaneous dipole in atom B. So, intermolecular forces is caused by the attractive forces because of the temporary dipole. You have also to realize you don't have to have it between 2 molecules. If you place a cation, in this case a positive ion, that positive ion will create an attraction for the electron cloud in a nearby molecule. Therefore, you have an unequal distribution created by the cation. This is called an induced dipole because the cation is creating or inducing a polarity in the nearby molecule. And there's going to be an attraction there. The cation becomes momentarily attracted to the negative pole of the molecule. Now what happens is if you have a permanent dipole, an idea that we'll discuss in a moment, a permanent dipole is where it's a molecule, but one side is permanently negative and one side is permanently positive. You can think of a water molecule. A water molecule is a permanent dipole. One region is always negative, the other region is always positive. If you're wondering how does that happen, it has to do with electronegativity, meaning that there's a greater pull on the electrons on one side. So a permanent dipole can cause what is normally a nonpolar molecule to momentarily have a dipole caused by the polarity of the permanent dipole. So the polarizability is based upon the idea that you, again, have increasing number of electrons makes it easier or more likely that you're going to get a momentary polarization. So more electrons, larger distribution, large distribution, more easily polarized because they're less tightly held and there's more of them. Again, you can think about the dance floor with a few dance couples versus a large number. Now, what you need to bear in mind that we can observe this by observing boiling points or freezing points. Pentane is a fairly small molecule. That's at the bottom. And you'll notice that its boiling point is below 40 degrees Celsius. As you move your way up to the hexane, heptane, octane, etc., there's a very linear increase in the boiling point. That boiling point increase is based upon the size. And as the increased size of the molecule, there are more electrons statistically that can become unequally distributed. You get a momentary polarity, you get a momentary attraction, and that traction holds the molecules together and makes it more difficult to pull them apart and go to a gaseous state. So the increased size creates an increased IMF, which is the intermolecular forces that hold the molecules together. Now, there's a second kind of attraction, which is the dipole interaction. In a dipole to dipole, the molecule is permanently polarized. It's permanently a positive and a negative side to it. And when it's mixed with another polar molecule, those polar regions line up and attract. And they're referred to as a dipole to dipole interaction. They're permanent and they're fairly strong. So what you see here is the attraction on the left is when it's in a solid state. You'll notice it's very orderly, which all the positive and negative poles are lined up. And if it goes to a liquid state, in the case of B, the spacing's more, there is movement possible, but you still have a lot of attraction. So dipole to dipole molecules, again, you could think of water as an excellent example. Those attractions are very strong, and because of that, it's actually hard to turn them to a liquid and then turn them to a gas because the molecules are held together. So take a look here. You have a formaldehyde and you have ethane. Now take a look at formaldehyde. Its formula is CH2O. You could see the structural formula. And you'll notice that the boiling point is minus 19.5. And the melting point is minus 92. Now take a look at ethane. Ethane is not polar. It's a nonpolar, and its boiling point is minus 88. Now, crucial, the formaldehyde boiling point is higher than it is for ethane, and that's because the formaldehyde molecules are polar, and therefore you get a lot of polar dipole to dipole interaction. They're held together well. It's hard to pull them apart, and so the boiling point is actually fairly high. Ethane, on the other hand, which is nonpolar, it has only the London dispersal forces or instantaneous dipoles. They're not held together very well. And so it's relatively easy to make them go to a boiling point or look at the melting points, compare those. So that's your difference of the amount of strength that interaction between molecules, ethane, which is a nonpolar, and formaldehyde, which is polar. So the dipole forces are greater, and therefore it's higher. Now let's take a look at this here. What you're looking at is you're looking at a degree of polarity from propane, which has virtually none, all the way up to acetonitrile. And you see an increase in the boiling point. Note, by the way, that's in Kelvin. So you see a greater increase in the boiling point because you have a greater and greater degree of polarity of the molecules. The third kind of interaction between molecules is hydrogen bonding. Here in hydrogen bonding, and it's really crucial you look on the left-hand side, the hydrogen bonding, in this case, is between water. And what it is that the oxygen are very polar in that they have a lot of negative charge to them. Hydrogen of the other water is polar positive. And there is a pull, a very strong pull, between the oxygen of one molecule of water and the hydrogen of another water molecule. And that pull or attraction, that is the hydrogen bond. You'll notice that nitrogen, that's in the molecule ammonia, can create the same property, and you're going to see hydrogen bonding. What you want to make sure you recognize is hydrogen bonding stands out when there's oxygen, nitrogen, or fluorine involved. So if you have the NH, or you have OH, or you have FH, you immediately got to think, I've got a hydrogen bonding situation, and because of that, I should see a high boiling point, I should see a high melting point. So NOF, That's where you're going to find the hydrogen bonding taking place, and that is where you have very strong polarity. And again, when you have that, there's very strong molecular attractions going on. So now what you have is a diagram illustrating the hydrogen bonding in action. So once again, let's take a look here. Ethanol has a boiling point of a 78, and dimethyl ether has a boiling point of a negative 22. Now you might be thinking, but I have an oxygen in there and I have hydrogen in there. I have hydrogen bonding between both of them. Why is there a difference? You'll notice that the oxygen is sitting on the edge of the ethanol. What that means is it's extremely exposed. So it can exert a pull very effectively with another molecule. And the result is the attraction is much stronger there than it is for the dimethyl ether. Now, on an exam or whatever, do I expect you to pick up on that level of subtlety? No. But it does try to point out that when you do get these polarities, its position does matter in the molecule. Now, hydrogen bonding is a special dipole-to-dipole interaction. And the reason for that is because it is in fact so strong. You could see the H2O, HF, NH3, HCH4. You can see how strong of an impact it does have on boiling points of the other molecules. Here again, you'll notice, working your way up the chart, NH3, look how much higher it is compared to the other. H2O, look how much higher it is. HF, look how high it is. Those are very, very strong hydrogen bonding attraction between them. Now, hydrogen bonding is profoundly important in a biological molecule of DNA. What you'll notice is between the adenine and thymine, which are the base pairs in DNA, you have hydrogen bonding that holds those two together. So the entire molecule of DNA, the two sides, are held together by hydrogen bonding between the adenine, guanine, cytosine, and thymine. Now, ion and dipole forces. We briefly talked about this already. When you dissolve an ion in water, the strong polarity of water causes it to be attracted to the ion that's inside the water itself. It creates a orientation, and there too it's very, very strong. When you have an ion dipole force, you have a Na+, and if you have a fixed dipole, negative to positive, or if you have I-, the dipole flips around, you have an attraction. And again, that's a very powerful attraction between them. So, in summary, you have four major types of attractions. You have dispersion, which are instantaneous, unequal distributions of electrons in the molecule itself that creates an instantaneous attraction for nearby molecules. These are your London dispersions, also called the van der Waals. They hold most often the nonpolar to nonpolar molecules. The larger the molecule, the stronger this is. And because it's stronger, larger molecules tend to have a higher boiling point or a higher melting point. Dipole to dipole, these are permanent dipoles. They have permanently oriented positive and negatives, and they have a very strong attraction. Again, that will make a higher boiling point and a higher melting point. A unique or particularly strong dipole to dipole is a hydrogen bond found in water and in nitrogen groups and in fluorine groups. And finally you have the ion linked to a dipole. This is very common in aqueous solutions. So intermolecular forces determine the state gas, liquid, solid, weak, moderate, strong forces. IMF, which is the intermolecular force strength, it gets stronger. As it gets stronger, then the melting and boiling temperatures tend to be higher. Last idea, when you look at a protein in terms of biology, all forces are present. You see hydrogen bonding, you see dipole to dipole, you see van der Waals forces. So molecules of the protein type in biology, which are enormously complex, are involved in all of them. Ionic, hydrogen, and dispersion forces, dipole to dipole.